Okay, so here in our second video, we'll look at how you actually use a power series to solve a differential equation. So what I have here, if I had to classify that, that'd be what turns out to be a non-homogeneous second order linear differential equation. And I think we can solve it by the method of undetermined coefficients if we want to. But it's also, as far as power series solutions go, fairly easy to solve with a power series. So here's what we do. So I give you that, and that's the differential equation you want the solution to. Apparently, I'm telling you that x is the independent variable, and you're going to assume that that's the solution. We do that all the time. When we solve differential equations, the process normally starts with us assuming this solution takes a certain form, and that's what we're doing there. There's a power series centered at 0. Okay, now I'm going to make this work up there, and I noticed that if that's y, and if I need y double prime, I have to appeal to the rules of calculus, and I'll find that this series, term for term, is the derivative of that one. Okay? You can write that thing out if you want to, differentiate it term by term. You'll get this series. It will start at 2 n times n minus 1 times an for your coefficient, and then x to the n minus 2 power. Okay. All right, so there, I needed that in order to start working this out. So what's that look like? Okay, so here's your differential equation with the assumed solution operating inside of it. So I get this. Here's my y double prime. Okay. Subtract constant of 1 equals 0. So what do you think you do with that? Well, I guess knowing the solution here would just amount to knowing those coefficients. If I knew what they were, I'd have it. So if there's only some way to find the coefficients, well, we've got this thing I called the coefficient theorem for power series. We have a power series starting with a constant term, then a coefficient times x, a coefficient times x squared, so on. If that's 0, then every coefficient is 0. So I guess when I do this, I just aim to say that somehow about the coefficients. I can't do that here. This is not a power series with all terms arranged in order. Where's this one begin? That's a power series, but this starts with the constant term. So I'd have to group that together with this one. And then say I took the constant term out. Well, then the next term would have order x to the first power. So in order to arrange it so that I can see that I have a power series and I can identify what the order of every term is, then I can set them to 0. I'm going to have to take out the constant term. So here's my my impression of what to do. Let's take away what would be the very first term of this series, which is a constant, is 2 times 1 a2 times x to the 0 power, which is 1. We'll have to take that one out. Okay? And we'll put it together with this. And then you'll see that we get a power series and our terms are in order and all accounted for. So here goes. Say if we take that away, what's it going to look like? Well, if you take away this first term, then you'd pick up from here at 3. So we say n is equal to 3 to infinity. And that's not going to change how you get the other terms. It's still n minus 1, an, x, n minus 2, plus, okay, that's a constant, and so is the 1. So we'll say 2a2 minus 1. And now I feel like I see everything. This entire expression is a power series. this would be the constant term of the power series. Picking up over here, you will get your term of order x to the first power, then x to the second power, and so on. So it's all there. And in that case, what would every coefficient have to be? Every coefficient have to be 0. So the constant term would have to be 0. We would say 2a2 minus 1 is 0. And so that puts a2 to be a half, all right? And then every coefficient here would have to be 0. So here's what we'll say. We'll say n minus 1, an, that's the coefficients, right? Those are all 0. Okay? All right, so, well, all right, I get an is 0 by n times n minus 1, which is 0. Okay? 0 for what? For n going from 3 onward. Oh, so a sub 2 is a half, but a sub 3, 4, 5, 6, and forever just aren't there. It doesn't say anything about a1. No? I don't get anything out of this about a1. Doesn't say anything about a2. Nothing up here is going to tell me... Oh, sorry, I messed that up. Doesn't tell us anything about a naught. Nothing up there. There's no information about it. That might seem strange, but let's do this. Let's do this. We know this, and we know that. Okay, what's your solution? Okay, here it is. Y is equal to, what's that power series going to be? A naught? I don't know what that is. Okay, plus a1x. I don't know what that is either. Plus a2 was a half, so 1/2 x squared. Well, so there's your general solution. Now, is it a problem that we could never find those? No, because when you solve a differential equation, as we know, there will be constants in the general solution. And we won't find those unless we have initial conditions. So that's all a naught and a1 turn out to be. Okay? If you want to, we could write this solution the way that we used to write solutions to second order linear differential equations. You could say, here's something that's going to work. Some arbitrary constant c1 plus some other arbitrary constant c2 x plus 1/2 x squared. Okay? So, well, either way, right? What we're getting now, we used to write like that. Okay, so there's my answer. That's at least the general solution. We don't have what we need to find the particular. But it's not an issue if you, say, can't find two constants out of that. Because we weren't ever able to. The general solution ought to have two undetermined constants. So you find that answer, what we get right out of the power series, is really no different than the kind of answer that we would have gotten when we first started learning to solve these.